So here we are in Unit 3. It's all kind of downhill from here because before you know it, there's going to be oxygen in the atmosphere, and then there'll be life. Well, there's life, but there'll be multicellular life. So, and that is going to happen in this chapter on the Proterozoic Eon. So, with our clock diagram of geologic time, I want you to see why the Proterozoic Eon is put in a new unit. It represents 42.5% of all history of the Earth. Lots of really important things happen in this eon, so much so that it's subdivided into the Paleoproterozoic, which means the ancient Proterozoic, and then the Mesoproterozoic means the middle Proterozoic, and then finally the Neoproterozoic means the newest part of the Proterozoic eon. And you will see that there's a lot of ways and reasons that it is chunked up in that way. So the Paleoproterozoic starts at the end of the Archean eon, 2.5 billion years ago, and it goes to about 1.6 billion years ago. And it's characterized by a couple things, but one of the most important is the accretion of continents. Remember that accretion means that we're kind of adding land together. We talked about accretion when we first talked about planets forming, where we had planetesimals accreting to form protoplanets. And then we talked about accretion again when we started to talk about the creation of continents, when we had island chains that were combining together. And continental accretion is no different. It is the growth of continents where we have the suturing together of some of our Archean provinces. So the growth of those Archean cratons together in North America created a landscape that geologists refer to as Laurentia. So this is a paleogeography map, and they're made by this retired geologist Ron Blakey at Northern Arizona State College. And so he used Google Earth images as well as modern geography to kind of put together what the Earth looked like at different time slices. They're beautiful. And so this is a Paleoproterozoic map of North America, which is part of a land mass known as Laurentia. You can see that north is actually oriented in this direction on this map, which means that North America, or Laurentia rather, is just south of the paleo equator, and it's rotated quite a bit from its modern configuration. Laurentia is mostly North America, but what you can see in the outline here is that it's also comprised of Greenland, Scotland, and pieces of Scandinavia as well. And so part of the way that continental accretion occurs are through smaller orogenies. Remember, orogeny means mountain building event, like the Watmay orogeny, which has been dated to 1.9 billion years ago and is in northern Canada. So here you can see the Watmay origin, and you can see that it helped to suture together pieces of the Slave Archean province, which we talked about last unit when we talked about granulite and greenstone belts. So this is actually the first good evidence we have of a Wilson cycle. You'll remember Wilson cycles are the idea that ocean basins will open and close. And so that opening is characterized by divergence. We can see evidence of divergence in this cartoon cross-section of part of the Watmay origin. So let's take a second here and just kind of take it all in, and then we'll walk through what we see. So down here, this portion of the diagram, you can see a series of faults. And if you remember from 101, the hanging wall is the block above the fault. Oh, it's going to happen. Turn on my pen. Okay, so if we look at this fault, the hanging wall is above the fault here, and then the footwall is down here. And we can see based on the orientation of these blocks that the hanging wall moved down. And the hanging wall moves down on what's called a normal fault. Normal fault is the result of extensional or divergence, extensional stress or divergence, which is cool. We also see that there are some basaltic lava flows as well. That's another clue that there is divergence going on, because as crust gets thin, because it's being stretched, like during rifting, it will cause decompression melting in the upper mantle, which will cause basaltic lava to erupt up through these faults. And that's what we see here. So this is all evidence for ancient divergence right there. I like that. It was like a spear. So the normal faulting that we see indicates rifting of the Archean crust. So do these basaltic intrusions. And then remember, if we're talking about land being split into two pieces at least, as they're split, those two pieces of land are also going to shed sediment into that ocean basin in between. And we can see that represented from the sediments that would have been deposited from the erosion of those surrounding land masses. And so we see that as we look here, where we have some sand that is deposited as those two pieces of land were close together. And then as those two pieces of land drifted further apart, and the source of that sediment becomes more and more distant, we start to have the formation of carbonate materials. So remember, this connects back to the idea of a marine transgression as those pieces of land are moving farther away, where we have coastal sediments being deposited here in the sandstone, overlain by deeper water carbonate sediments. So there's our evidence for divergence. However, when we look at the way that the Watmate origin looks today, we have to find evidence for convergence as well. And we see that in the way the rocks look today. So we have some intrusive rocks, which are typical when you have two chunks of land colliding, that you might have any magma chambers sort of ease their way up and cool. And then we have some strongly deformed metamorphic rocks, followed by some folded and faulted rocks over here. So conversely to what we saw on our last slide, when we look at these faults, the hanging wall is up here, and right in the hanging wall moved up here, so that means not extension, that means compression, and then the footwall is down here. So when the hanging wall moves up, those are called reverse faults, and when it's a low angle fault, here's a new term for you, when it's a low angle reverse fault, like less than 30 degrees, geologists call those thrust faults. And now I'm going to get rid of my pen. So how can we interpret these rocks? Well, it's very common for sedimentary rocks upon convergence of continental land masses to form folded and thrust faulted rock here. We see that when we look at the Appalachian Mountains in Virginia, for example. We see rocks that look deformed in this particular way. It's the same type of rock and generally form folds and thrust faults. In the zone of maximum convergence, that's where we have our strongly deformed metamorphic rocks. So this is how our continental land masses are going to be accreted together, where we have first stretching of the crust and then collision of those Archean provinces that get stitched together during the Proterozoic Eon. Another example of this, also in northern Canada, called the Hudsonian Origin, which is 1.5 billion years ago. And you can see that right here. And the Hudsonian origin here stitched together the Superior Craton as well as the Wyoming Craton here. And this is just another vantage point. It's a little bit less confusing of a map, but also less informative. So you get both. The other thing we have our very earliest evidence for in the Proterozoic Eon is the first ice age on Earth. The first ice age seems to be recorded in rocks about 2.6 to 2.1 billion years ago, and the rock that most directly shows evidence for that ice age is the Goganda Formation. The Goganda Formation is composed of a series of rocks, including conglomerates and laminated shales, and those are believed to represent ancient examples of glacial varves. So let's talk about what those might be. Here's a picture of the Goganda Formation, and you notice that there's all sorts of mixed up rocks down here, followed by really sort of rhythmic and predictable layers of rock. And so these are your laminated shales here. They are interpreted to be glacial varves. This is the conglomerate layer down here. Here's a modern example of some glacial varves that were deposited during the last ice age. So glacial varves are interpreted to be ancient glacial lakes. And in the last ice age, we have tons of evidence for them in North America. So during the summer months, when it's warm and when rivers are depositing a lot of sediment into lakes, lakes tend to deposit thicker layers of sediment that are coarser in grain size than one gets deposited during the winter layer, which makes sense, right? Because there's less discharge from the rivers during the winter because there's so much more precipitation that is stored as snow and ice, right? Collectively, these are called varves. Varves are seasonal layering that we see in lakes. And so here, just like when we study things that are in the modern and then we apply it to the ancient, we are doing the same thing in the Goganda Formation. So these varves are interpreted to be glacial lakes. Glacial lakes are common when you have melting glaciers, right? You have a tremendous volume of water that is melted off and it creates a series of lakes in front of large glaciers. So the conglomerate layers that we see are alternating with rocks that look like this, which are often called tillites. So glacial till is the rock here that is lithified. So glacial till, if you remember, is rock that kind of gets bulldozed over land when glaciers advance over a location, because rock gets eroded from higher elevations and then it just kind of gets dragged to some of those lower elevations. So the tillite here represents glacial advance. And then when the glacier starts to melt, it deposits glacial varves because there are glacial lakes, and that's retreat. So this Goganda Formation seems to record that same thing that we see in the modern with periodic advancing and retreat of glacial lakes in response to glacial advance and retreat. All right, so we're going to practice some graphing skills in our next assignment, and then we're really going to talk about how the world became an oxygenated planet.